First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
Okay, greetings. Today we're going to look at the DIS method again. This is the part 4 in our DIS method series. And before we get going on this part 4, which should be fairly straightforward, we're just going to kind of review the progressions that we've made thus far. So in part 1 of the DIS method, we basically had a curve which was being rotated about the x-axis. And so this curve was of the function y equals f of x. And just to put upon, so when we revolve something about the x-axis or any horizontal axis, our function is of the form, the function that models our radius is of the form y equals f of x. Our curves are x equals equations, and our axis of rotation is actually a y equals equation. Here it's designated as the x-axis, but the equation of the x-axis, of course, is y equals 0. So this is what happened when we revolved it about the y-axis, and then we revolved it about the x-axis, and then we revolved it about a horizontal axis of the form of y equals k, and it just changed up our formula ever so slightly. And again, in that part 2 video, we show why this occurred. But basically what happens is we're taking the difference of the function in k, the value of the horizontal line which is being revolved about, and simply squared it. So if it's revolved about some horizontal line of the form y equals k, we're going to have pi times the integral from a to b of f of x minus k whole squared. And again, if I'm revolving it about a horizontal axis, my function is going to be of the form y equals f of x. My limits are going to be x equals form, but my axis of rotation is going to be of y equals form. And so in our part 3 video, we looked at rotating about the y-axis. So now when we go about the y-axis, we're now rotating about a vertical axis. And so now our function is of the form x equals f of y. Our limits are y equals equations, and our axis of rotation is actually an x equals equation. So today what we're doing is we're going to be rotating the curve about a vertical line of the form x equals k. And so if you just think about the progression that's been made thus far, particularly the progression from the x-axis to a horizontal line y equals k, then it should be easy to see what's going to happen from the y-axis to a vertical line x equals k. And that is that we're simply going to have pi times the integral from a to b of f of y minus k squared dy, where of course k represents the vertical line. The vertical line is of the form x equals k. So this is our part 4 video. At this point, a lot of what we do with the DIS method should be fairly routine if you've been catching on. So I'll go through 2 examples. I'll go through them fairly quickly. It's not going to be a whole lot to elaborate on, kind of just watching the process, and this should make clear sense. So let's go through a couple of examples. All right, so this is my first example. If I can read it, it says find the volume of the solid generated by revolving the region bounded by the graphs of y equals the square root of x, y equals 0, and y equals 3 about the line x equals k. So again, we're going about a vertical line of the form. I said x equals k, excuse me, in particular x equals 2. So we're rotating about the line of the form x equals k, and this k is 2. So we have, this is my axis of rotation, x equals 2. Of course, it's vertical. The value of k is 2. And when I have a vertical axis of rotation, my limit should be of y equals form. And so y equals 0, that's A, and y equals 3, that's B. And my curve should be of the form of x equals f of y, x equals f of y. So I'm going to take this curve, so the curve is y equals the square root of x, and put it in x equals form. So if I have the square root of x equals y, and I will square both sides, and we'll get x equals y squared. So therefore my f of y expression is y squared. So now I know everything I need to know. I know f of y, I know a, I know b, I know k. Now it's time to put the guy in a formula and see what happens. So therefore, the volume here is going to be pi times the integral from 0 to 3 of y squared minus 2 squared And so that's f of y minus k squared. So I like to expand before I integrate. So I'm going to expand, integrate, and then evaluate, and then we will be presented with our answer. So if I expand this particular integrand, so the integral from 0 to 3, that's going to give us y to the 4th minus 4y squared plus 4 dy. Okay, so that should be fairly routine. So next thing, of course, is to integrate. We'll integrate by the power rule. That will give us y to the 5th over 5, 4y cubed over 3, and 4y respectively. Let me go ahead and write that. So this is pi y to the 5th over 5 minus 4y cubed over 3 plus 4y to be evaluated from 0 to 3. So in this case, I think it's fairly obvious to see that if I plug in 0 for y, I just get 0. So I really only have to plug in 3 for y to find my answer. So let's plug in 3 and see what occurs. So 3 to the 5th is 243 over 5 minus 3 cubed is 27, divided by 3 is 9, times 4 is 36. And 3 times 4 is 12. So negative 36 and 12 is negative 24. And if I want to write that as a fraction with a denominator of 5, 24 times 5 is 120, so that'll be negative 120 over 5. So this is pi times 243 over 5 minus 120 over 5. And so that should give us 123 pi over 5. All right, so that's example number 1. Again, we're only going to look at 2 examples because the process is so similar to what we did in parts 1 through 3. All right, so let's go ahead and look at the second example. And so I'll go ahead and read the problem. So it says, find the volume of the solid generated by revolving the region bounded by the graphs of y equals ln x, y equals 0, and y equals ln 2 about the line x equals 1. All right, so we're rotating about the line x equals 1. Again, this is my axis of rotation. So the value of k is 1. Again, and this is a vertical axis of rotation. When the axis of rotation is vertical, my limits are a y equals form. So that means my a is 0 and my b is ln 2. My main curve is of x equals f of y form. So the main curve here is y equals ln x. And so we're going to put that in x equals form. So let's say ln x equals y. And you can either just rewrite this in exponential form if you're familiar with that, or you can exponent both sides, make this e to the power of ln y equals e to the power of y, and of course, e to the power of ln x equals e to the power of y. And of course, e to the power of ln anything is anything, so e to the power of ln x is simply x. So x equals e to the power of y. So our f of y function is e to the power of y. All right, so now we know our f of y, we know our a, we know our b, we know our k. We're ready to put it together in the formula, integrate, evaluate, and obtain a sufficient answer. Okay, so b is going to be pi times the integral from 0 to ln 2 of e to the power of y minus k was 1, I believe, minus 1 squared dy. We want to never forget the pi when doing this method. We want to never forget that we're squaring the guy, and if it's about some, something of a form of x equals k or y equals k, we don't want to forget to subtract the k in whole being squared. Okay, so let's expand this first. So pi integral 0 ln 2. If I expand this, I'll get e to the power of 2y minus 2e to the power of y plus 1 dy. And so now we can integrate and evaluate. So calibrate. integration was slightly off. So if I integrate this guy, whoa. So if I integrate e to the power 2y, I should get 1/2 e to the power 2y. The integral of minus 2ey is just minus 2e to the y, and of course integral of 1 is going to be y. And so that's going to be evaluated from 0 to ln 2. All right, so in this particular problem, we are going to have to plug in a 0 because, e to the power 0 isn't 0. So plugging in 0 does not give a 0. So we're going to plug in both ln2 and 0 and take the difference of those two values. So let's go ahead and plug in ln2 and see how that works. So if I plug in ln2, I'll get 1/2 e to the power of 2 ln2 minus 2 e to the power of ln2 plus ln2. All right, so that's what we get for plugging in ln2, and then minus, and now we'll plug in 0, and we'll have 1/2 times e to the power 0. E to the power 0 is 1, so that's simply 1/2. And then minus 2 times e to the power 0, so that's just minus 2, and then 0. All right, so we have the following expression. And so we're going to simplify this a little bit. Now, just really one thing to look at is this guy right here. And so this e to the power of 2 ln 2, we know e to the power of ln anything is anything, but there's a number in front. So we can use our properties of logarithms, and we can think of e to the power of ln 2 as e to the power of ln 2 squared, or e to the power of ln 4. So we can do that based off the properties of logarithms. So of course, e to the power of ln 4 is simply 4. So e to the power of 2 ln 2 is simply 4. And so let's continue our calculations. And so we'll have 1/2 times 4, which of course is 2. All right, and e to the power of ln 2 is simply 2, and 2 times 2 is 4. So minus 4, ln 2 stays ln 2 minus, and now here we'll have 1/2 minus 2. 1/2 minus 2 is negative 3 over 2, but we have that minus sign, which will make it positive plus 3 over 2. So we'll combine our constants. Well, they're all constants. We'll combine our regular numbers. So 2 minus 4 is negative 2. So you have negative 2, which you can write as negative 4 over 2, and 3 over 2. That's going to give you negative 1/2. So we'll have pi times ln 2 minus 1/2. All right, that's the bottom of that particular guy. All right, so that will conclude our part 4 video on the disk method. Hope you enjoyed it, hope you understood, and we'll deal with the washer method next.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.